see exactly what attention does. One tiny PyTorch block that makes transformers click. By the end, you will have an intuitive grasp of self-attention and see the tiny pieces that turn token vectors into focused, context-aware outputs. I'm Professor Pi, teaching AI foundations with simple Python. Transformers became the go-to when you need models that read sequences and decide what to focus on. Self-attention is the mechanism that lets a model weigh different tokens against each other. Practically, that means better translations, summaries, and question answering for the same sized model architecture. If you have a few thousand training examples or a pre-trained backbone, attention brings large quality gains without exotic pipelines. At a high level, self-attention asks 3 questions for every token. First, how do I express the token as a query that looks for relevant information? Second, how do I represent potential targets as keys and values? Third, how strongly should the query match each key? And how do those strengths mix the values into a new token representation? Imagine a short sentence where the word dog needs to borrow traits from the word running. Attention computes those borrow weights and sums the value vectors accordingly. We will build a tiny end-to-end example so you can hear how each step affects the result. The code uses PyTorch tensors to keep things concrete and efficient. You will see raw similarity scores. Convert them to a probability distribution. Pick the strongest target, adjust sharpness, and finally combine values into the attended output. That prepares you to drop this block into a toy transformer or inspect a pre-trained model. Now, we compute raw similarity between queries and keys. This snippet computes scaled dot product similarity logits in PyTorch. It starts with a batch of query vectors and a batch of key vectors, and multiplies queries by keys to get similarity scores. The key idea is simple. Higher dot product means more alignment in the embedding space. The snippet usually divides the raw dot products by the square root of the key dimension to keep the scale stable as vector sizes change. That scaling prevents gradients from vanishing or exploding in larger embeddings. In practical terms, you will see a matrix of logits where each row corresponds to a query token and each column to a key token. Those numbers are raw affinities we will turn into weights next. Next, we turn those affinities into a distribution that sums to 1. This snippet converts logits to attention weights using PyTorch softmax. It applies a softmax across each query row, so the numbers become non-negative and sum to 1, which lets us treat them as how much attention each key deserves. Softmax amplifies the differences between logits, and if one logit is noticeably larger, it will get most of the mass. In debug runs, you can print a single query row and see values like 0.1, 0.3, 0.6 that sum to 1. Changing the axis across which softmax runs only changes whether attention is normalized per query or per key. And here we normalize per query to get a proper distribution of focus for each output token. Now we inspect which key gets the largest attention for each query. This snippet finds the strongest attention target with PyTorch topk. It selects the index or indices of the largest attention weights per query, giving you an explicit pointer to the most relevant tokens. The topk call is useful for diagnostics, for sparse attention strategies, or for routed attention, where only a few keys contribute. When you choose the top one, you force hard attention, which can speed up downstream computation, but loses soft mixing information. If you pick the top 2 or top 4, you retain more context while still focusing compute. The snippet returns indices and values, so you can inspect which tokens the model prefers and how confident it is. Next, we control how peaky or smooth the attention distribution is. This snippet sharpens attention with temperature scaling in PyTorch. Temperature is a single scalar that divides the logits before softmax. Lower temperature makes the distribution peakier. Higher temperature makes it flatter. In practice, a temperature of 1 is the default. Dropping it toward 0.5 or 0.2 pushes mass to the top entries and approximates hard attention. Increasing it toward 2 or 3 yields more uniform mixing across keys. This brief adjustment is powerful when you want a model to either focus tightly or gather broad context without changing the underlying vectors or training regime. Finally, we build the attended outputs by mixing value vectors. This snippet builds self-attention outputs by weighting values in PyTorch. After you have attention weights, you multiply them into the value matrix and sum across keys for each query, producing a new vector for every token that blends information from the sequence. Conceptually, this is a weighted average where the weights came from similarity between queries and keys. The code typically uses a batched matrix multiply, so the operation runs fast on GPU. The result is a tensor of the same token count, but with context embedded, and you can inspect one output vector to see how it shifted toward features from its top attention targets. This toy example maps directly to a real system if you swap in real token embeddings. In a translation pipeline, you would compute queries, keys, and values from the same embedding layer for self-attention. In an encoder-decoder setup, you would cross-attend decoder queries to encoder keys and values. The tiny block we just examined is the building block that scales up to very deep language models. Recap. Self-attention computes similarity, turns it into a distribution, optionally sparsifies or sharpens that distribution, then uses it to mix values into context-aware outputs. Use it whenever tokens need to consult each other, like translation or long-range context tasks. One caveat: attention is quadratic in token count, so for very long sequences, you need sparse or approximate tricks. Next step: scale this exact block to a larger token window and time it, comparing temperature settings and a topk sparsity cutoff to see trade-offs between speed and quality. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.